Well, howdy, physics sleuths and inquisitive souls, and welcome again to yet another lecture of dynamic gravity. It appears as though you were deep in your slumber last night, sleeping like a baby. I was up late, doing an all-night bender with all the drugs. All of them. And my God, Lord Shiva has revealed all to me. All of it. The final layer of the onion peeled back for me to observe and learn. And I'm going to show you everything. And that will be it. There will be no more mysteries left in physics that I have not explained to you thoroughly. You see, today I'm going to go over quantum spin one more time because there's one additional element that's very important that I was missing, and also how this creates magnetic fields. Okay? There's a lot more going on, and I'm going to have to do another video probably in a couple weeks. It's going to be field theory. We're going to go deep. I'm going to have to come up with new terminology to describe what's going on. That's how deep we're fucking going, my boys. And it's rock bottom. There's nothing more. We are going to be explaining what the fuck an electric field and gravitational field actually are, what they're made of, how they're created and generated, and what the fuck is all going on with that. I got it all, baby. I got it all. But first, I don't have it all. I need a soda. I'll be right back. Woo! Sorry about that. It's always when you think you have everything that you realize you don't have everything. But then you do get everything because then you know what the one thing was you were missing, and that's how it works out sometimes. So, all right. So, I'm currently writing my fifth paper, physics, that's going to explain all this stuff. Hopefully I'll be done in a week. We'll find out. I honestly thought it was going to take me a lot longer to figure everything out, like everything. But when you have God on your side helping you out and you're listening to Him, I guess anything's possible, right? So, we should probably start digging into this a little bit piece by piece. And this is going to be one doozy of a lecture, so just chill the fuck out. Grab a drink, make it a stiff one. You're gonna need it, and let's just sift through this rabbit hole, 1 inch crawl at a time, and that's how we gonna do it. All right. So, let's see here. Let's go here. All right. What the hell is this shit? What the fuck was I looking at? I got no explanation. Alright, now, if you've ever seen my channel before, you know that what particles are, like electrons and quarks, okay? And even neutrinos, and what else have we got? There's something else in there too. They're all just vortexes, alright? They're vortexes of electromagnetic radiation for like an electron. For a quark, it's a vortex of gravimetric radiation, okay? It's all they are, and that's how they're made, is the fast-moving motions that cut through back and forth to make the disturbances, and you have a new secondary particle. it behaves, just like the identical. But you see how it goes, and it has, its own boundaries, but yet it's made up of something different. But now the rules that go into vortexes are also the exact same set of rules called the Biot-Savart laws that determine magnetic fields, which is essentially disturbances, an electric field, which is what I'm saying, like say the particle boundary is. So it's all the same mathematics. It's all there, right? Now, these electrons, okay, let's say this is an electron, right? We got a tori, a torrid with its spinning, okay? We're going to have to draw this because this is going to get cray-cray, all right? Now, okay, this is good. This is actually good, okay? Let's say this is the electron, right? Obviously, I made this electron, okay? And it's spinning like this direction, okay? It's spinning in on itself, and it's going very fast, like 1% the speed of light, and it's very strong and sturdy, okay? So it's made up of an electric field, okay? And in a week or two, I'm going to tell you all about the electric field and what's going on with that and everything. But just for right now, just know that's the lowest level we're working on is the electric field, okay? So we got the electric field, and it's spinning rapidly. It's making these circles, right? They go do, 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 like this, okay? All around this donut tori, okay? And what that's doing is there's a thing called the right-hand rule, okay? Now, I learned it the right-hand rule, and I was always confused by it. And I'm like, what the fuck is this bullshit? It's much better if you think of it as the right-hand curl, okay? The right-hand curl, all right? This is all spin and spin and spin. All right, the right-hand rule, okay? But it's also this, the conventional direction of active rotation. So anything that's spinning, which electrons are definitely 100% spinning, I'm going to prove it to you, all right? Don't worry, we're going to get there, all right? The best way to think of it as the magnetic field generated from this particle as it's traveling and spinning is going to make the magnetic field have a spin function to it, okay? So it's going to have a spin, the magnetic field, okay? If you were to plot it like around the wire, okay, this is a good one, right? Now, do you see how we have the wire here, okay? So the current is going this direction of the electron, all right? And so the field is going to be spinning around this way, counterclockwise, okay? So what it's saying is that as this magnetic field is being, pushed out in a circular fashion like this, it's going to be spinning this direction, okay? Everything is going to be spinning and experience force that's pushing it around, like a circle around the wire, okay? And that's the right-hand rule, okay? Now, I explained what was going on a lot with magnetic fields like a couple years ago, and I couldn't go any deeper than the level of a right-hand rule because I didn't know why the right-hand rule was the right-hand rule and what's going on with field theory. Now I do, and so I'm explaining this to you, okay? So now we're picking up where we left off on my last video, which is a doozy, and we're going the final layer. We're ripping back the final layer of the onion to see what the fuck is underneath it all, okay? We're pulling the hood off the car, and we're going to see the engine in its totality, how it's working, all the mechanism, all right? So that's what's going on when you have, okay, that's how the forces are going, okay? Now, what is causing that spin of the magnetic field? It's spinning, okay? It's got force being spun this direction around the wire. What's causing that spin of the magnetic field is the intrinsic spin of the electron, okay? So, electron intrinsic angular momentum, okay? Electrons, as all matter, can have two spin states. It can be spin left or spin right, or spin up or spin down, however you want to think about it. Just opposites. Spin this direction, spin the opposite direction, okay? Now, it's long since been known that everything has been biased for the right hand. Like, why is it, my bad, for like electrons, why is it always spin up, the right spin that dominates everything? And we're going to go and explain a lot of this, okay? We're going to go pretty freaking deep on this, all right? So here, they're shooting electrons, right, with magnets, and because they have different spins, they're changing the course through this magnetic field. It's forcing them to follow different paths. One goes up, one goes down, okay? Now, this is all known, okay? And current physics says the electrons act as though they're spinning. They behave as though they're spinning, but we can't see how they could possibly be spinning because we don't even know what an electron is. It's classical physics for you. They don't know shit. I know everything. Listen to me. I'm going to get you there, okay? So, every electron, every particle has two spins, okay? If it spins this way, spin up, which would be this direction, spin up with the right-hand rule, spin this way, then you have a magnetic field that comes around this little particle like this, and that is what's interacting with like this experiment, is the magnetic field is created from that spin, okay? Now, I probably should have to show you this. Okay. Here is a diagram that I used for my last paper, and I added the actual spin mechanism going on this paper so you can see it, okay? Here you have two electrons, okay? They're in orbital. They're sharing the same orbital, so they're entangled. They're entangled electrons, meaning one's going to have a spin up state and the other is forced to have a spin down state, okay? Now, I didn't explain exactly what the difference was that was spinning, and truth be told, I hadn't even thought of it yet. I'm kind of, figuring all this out as I go, and I have to do it one step at a time. But if I'm right, everything is going to work out in the end, and that's how I know I'm right, because it's working out just like it's supposed to. Okay? So, here's, say, our nucleus right here, okay? Nucleus of atom. So you got like the dominant electron, it gets there first, okay? Now, the spin state of the electron is completely defined and generated by the nucleus of the atom, okay? So if you have an electron, it is naturally not going to want to be any spin left or right unless it's in the presence of an atom, where it's being subjected to the magnetic field pushing out of the nucleus, which is a positive entity that is indeed spinning, okay? Now, I can't tell you how much it spins or how often it spins, but it does spin enough to have a magnetic field that interacts with electrons. And we know this because there have been experiments to prove that the spin of the nucleus can actually change the orientation of covalent bond electrons. It means electrons that are bonded to its most outer shell that aren't even in its atom. So it's changing the spin state of other electrons, okay? That's how far out it can go. So anything in the atom is going to be affected by this. And I don't have this 100% sorted yet, but it's getting there quickly, okay? So we have the first electron gets there, right? Second electron gets there. And now they're both sharing the same orbital and they're entangled. And now you have the nucleus of the atom, okay? Now, I told you about the right-hand rule, okay? The right-hand rule is for negative charges, okay? There's another rule called the left-hand rule that's for positive charges. You swap the charge, I mean, you go from an electron to a quark or a proton, and now all of a sudden your rule gets inverted, like a chiral partner. It just flips its orientation completely, 180, all right? Like a mirror, all right? This is, I'm not making this up. This is all known science. This is totally all known science. In fact, let me see if I can tell you. But anyway, so I'll show it to you here in a second. I'm just going to get this out of the way. So we have the left-hand rule of the atom, of the nucleus, okay? It's spinning, and it's got its momentum going this way, and it's spinning around this way, which means it has a magnetic field, or gravimetric field, technically, because it's not electromagnetic radiation coming from that, it's gravimetric radiation. But, okay, still affected, though, right? So it's going to be spinning this way. And then we have our electron, right, which wants, we know most of them are right, spin up, spin right. So how is this going to work? This one's going this direction, and this one's going the exact opposite direction. Do you see? They're exactly opposite directions. But remember, I say that electrons, the momentum, the momentum in which direction the vorticity of how they spin in on themselves, right? Like when we had that smoke ring. That determines the momentum, the direction that the electron wants to travel at the speed of light. And it doesn't if it can't, because there's things it's interacting with, slowing it down in its wave, whatever. Right now, this electron wants to go to this positive core of the atom, the nucleus, but it can't. It's trapped in an orbital because there's already an electron in the proton that it's attracted to. That's the down quark. The down quark is an up quark and an electron that combined. This is known fact, okay? I mean, known science doesn't know this, but known science knows for a fact that when a down quark decays, it almost always decays into an electron and an up quark. Doesn't seem too fucking hard to find out what it's made of. But the Standard Model is stubborn and egotistical and doesn't want to reevaluate evidence. So it just assumes that it's a whole particle and then there's all energy levels involved. And blah, blah. They don't fucking know what they're talking about, okay? So, it is going to be upside down, wanting to go towards the atom, okay? So, we have the left-hand rule of the nucleus, because it's a positive charge, and it's spin going this way. The orientation of the atom can only be one direction, okay? Because an atom does not have an up or a down that can swap vice versa. The atom's orientation is always one direction, the way its internal structure affords it, okay? I don't know why that is, but that is the way it is. We've known this. I've known this since my second paper years ago explaining neutrinos, how they were created, and what photons are, okay, in relation to photons. I knew that the only way it could work out is if there had to be an orientation of the nucleus. Otherwise, it was impossible to explain how neutrinos are being made the way they're observed when fusion and fission occurs. But if there was an orientation to the atom, all of a sudden everything works out. And one of the problems I've had with trying to explain the magnetic field is you have an obvious spin bias, right, of the field. There's spinning going on. But how can you have asymmetric behavior, like spin going in just one direction, on a completely asymmetrical particle that comes from a completely asymmetrical atom? You can't. It's impossible. There has to be an asymmetry somewhere embedded in the system, or it is impossible to have an asymmetry pop up later on, like in the form of a magnetic field with a right-hand rule. Okay? That's the way it has to be. Okay? And so, as it turns out, how fortunate, I'd already found that asymmetry. All I had to do was rediscover it. So, what's going on here? We have the nucleus of the atom that has its magnetic field, gravimetric field going this way, okay? And now we have the electron, which is facing that, and it's going to be affected by the nucleus. So it's going to spin the electron the same direction that the nucleus's field is spinning, right? It's rotating. You get that right-hand spin, that spin up, okay? And if you notice, they're both going the same direction. So left-hand rule and right-hand rule go the same orientation when one is inverted, trying to go as close as possible to the other. Okay? That's how the force is being submitted on this, is through the left-hand rule, to make these electrons have this spin to go to this right. Okay? It goes off to the right. You see, it goes off to the right. It goes off to the right. Okay? So what that does is this electron is going to start spinning. And when this electron gets in the orbital, it has no choice but to touch this because they're entangled. The orbital doesn't give them any space to work with, okay? And so when that happens, now they're both spinning the same direction, okay? They're both spinning towards this left. They have this, what I call drift. I call it drift, okay? Technically, it's just spin. It's quantum spin. But when you say it like drift, you see how it was given that orientation. Okay? It's essentially drift. That's what's causing it. But it is quantum spin. Okay? So, they're both going this direction. Okay? Now, what happens when you take these? Okay? Remember, they're upside down. All right? So, let's say they're like this, okay? They're smacking into each other like this, and they're both going this, spinning this direction. If you take the other one and take it so they're both oriented in the same direction, now instead of them both spinning that way, they're spinning opposite of each other. One is spinning left and the other is spinning right. One is going to generate a magnetic field that has a polarity going up, while the other is going to do it going down. Okay? Because remember, I mean, here it look like an orb, because they don't know, but it's a tori, it's a torus, okay? That's what the shape is. But this spinning is what is basically, all right? Now, if you take both of these and put them back like that, now they're both going to be spinning the same direction again, okay? But then when you take them back side by side, now they're opposites. That is how we get left spin and right spin electrons. It is all from the will, or the force majeure, so to speak, of the left-hand rule of the nucleus, of what the nucleus is doing to create its own magnetic field, a gravnetic field, technically, if you want to get sure about it, okay? Now, once we have that spin, if it's an up spin, it's going to be doing the right-hand rule, okay? If it's a down spin, it's going to not. All right, so upspin is going to give you a magnetic field that's going to be spinning the direction we know all magnetic fields go. So, if this is the mechanism that is essentially creating magnetism, the right-hand rule, then it has to all be from upspin electrons. They're spinning like to the right, okay? But how can this be? Because we know that every time an electron shares an orbital, they both have opposite spins. So you should have just as many electrons with a left spin as you should with right spin, right? You have to remember what's going on, though, my son, okay? First of all, magnetic fields that are created like with the right-hand rule, electromagnets is what we're really specific on. Bar magnets also do that, but they do it with domains, and that's where the electricity flows around in circles in the little domain, okay? But we're focusing on electromagnets running a current through a wire, okay, and having that field generated around that wire, all right? So, we have a wire, okay? What is that wire going to be made up of? It's going to have to be a conductor of electricity. And conductors of electricity are conductors for a reason, because they have a specific amount of valence electrons that allow the flow of electricity, of electrons, to hop from orbital to orbital, from atom to atom, and to go down the line of the conductor, the wire made of the conducting material, which is going to pretty much be copper, okay? Copper. Silver is another good conductor, and so is gold. Notice they're all in the same group on the periodic table. This means they all have one valence electron in their outermost shell. Okay? One. That's what they got to work with. So, here we go. Okay, copper. One lone electron in this shell. Okay? And guaranteed he's going to be upspin. Okay? Because that's the orientation that the atom is going to put on him. As soon as he gets there, he's going to start spinning in that direction, because that's the way the atom conserves the most amount of energy. Okay? Excuse me. So, gold, silver, all the conductors that conduct electricity really well, that's what they're doing, okay? Now, what's going on here is the outermost orbital has one electron, okay? When we put current through a wire, that puts a force that pushes the electrons out of their orbitals and down the line of atoms, orbital by orbital, atom by atom. Bloop, bloop, bloop. So, what's happening is this atom of copper is like any atom in a conducting wire, okay? And someone turns on the juice, the current, electricity. So now you're going to have atoms or electrons. They're going to go bloop, and they're going to share this outermost orbital with this guy that's upspin, okay? But it's not going to be stable. The atom doesn't like it. There's too much electricity, too many other electrons coming, trying to push these out of the way, and blah, blah, blah. It's not a stable configuration. So the instant that the electron gets there, it's going to kick out the electron that was already there, the dominant electron. It's going to bloop, kick it out. And then another one's going to come in and bloop, kick that one out. And then one's going to come and bloop, kick that one out. And it's just going to keep doing that over and over. And what's happening is every time it does that, the atom forces that electron to be right spin or up spin. Okay? So it might be entangled for a second, but it's an unstable entanglement for the configurement of the conducting element, copper, gold, or silver. And it's going to immediately kick out that electron and spit it further down the chain. And so this is going to keep happening. So what ends up happening is the electron that stays in the orbital of the copper ends up being upspin, and the electron that was kicked out of the orbital ends up being the upspin. So all of the electrons that are moving through this conductor are all upspin. They're all the right spin, okay? Which means they have the right hand rule. Which means as they travel through the wire, the magnetic field is going to curl in a circle going this way, around the wire. That's where that spinning of the magnetic field is. And you might be saying, okay, but Sean, what is the magnetic field? I'm going to go into this really deep and hard on my other video and field theory coming up very soon. But for right now, to ease your simple mind, my child, the best way to think of a magnetic field is it is just simply a shock wave of the electric field. And I believe I did a video on this not too long ago detailing this. Okay? That's what it is. When the electric field gets compressed, that compression gets pushed out at a 90 degrees angle like shock waves do. And if you notice, the magnetic field is perpendicular 90 degrees to the electric field, the direction of the electric field going. That's because the magnetic field is a resemblant shock wave of the electric field. That's what it is, my man. And that creates a whole lot of things that we'll go into on other videos. Okay? So, why do moving charges? Blah, blah, blah. Yeah, see, here we go. Here is the left-hand rule. Okay? I showed you the right-hand rule. Right? The right-hand rule with an upspin electron. Okay? But if you have an upspin quark or proton, it is opposite. So it's the left. Instead of the right, it's the left. Okay? Just so you know, I'm not making this shit up. This is all known science. Okay? I'm just putting the pieces of the puzzle together to find out what the image is. Alright? That's what I'm doing. I'm sleuthing it up. Okay? Yep, here we go. And here is another, like an electron. You can see how the electron travels. The field is going a specific orientation around it. But this is not a good picture, okay? Because this makes it seem like the field is being generated all around the particle. It's not. It's a shock wave. It's only generated in the front of the particle. But because you have so many particles coming behind this particle and constantly, it drags behind and then it just envelops the whole thing. Okay? That's what's going on. All right? So, I think we hit everything, right? I mean, I'm looking. think we did for today. I think for today we did really good. Just know, this is probably the best image you'll ever see of what is going on with two electrons that are sharing the same orbital in an atom and are entangled together. This is it. This is what's happening. They're both canceling each other's momentum out by slamming into each other. This one wants to go to the core, of the nucleus, but it can't because there's already electrons there that won't let it, too much resistance. And the overall spin of the atom is pushing the spin of both of these going to this drifting left direction, which now gives you spin up and spin down states. The way conductors are structured are architecturally with all the valence electron, pretty much as I see it, the only possible outcome when you have electricity pumping through a conductor to create a magnetic field, how we do it, is that you're going to have all spin up electrons. They're going to be doing the work, which means you're going to have always a right hand magnetic field, which is why the magnetic field is always right oriented and not left oriented, and why it has that spinning. But just know, I do believe this is a very good explanation, or not explanation, but image to show your brain of kind of how the magnetic field is working as the particle is accelerating and compressing it and making a shock wave. So there's all that. I'm pretty sure that 100% sorts out quantum entanglement with my theory. 100% sorted out now. 100%. Excuse me. And it happens to also explain a lot of things, working with known things that we know, like the magnetic field of the nucleus being generated to the left-hand roll. So in a couple weeks, I'm going to go off into field theory, and I'm going to explain to you what the actual smallest bit of matter technically is. Right now, people think it's a neutrino. Wrong as fuck. Neutrino is like the same size as an electron. It's just a different. It's made of a gravity field instead of an electric field, and it behaves radically different because everything is surrounded with the valence electrons of negative electrons, not positive protons. Otherwise, it would behave more like electricity does. But it doesn't, because the world we live in. But, yeah. And then we're going to go deep into field theory next time, and we're going to come up with some new terminology, and we're going to hit rock bottom. That's it. That's the final layer of the onion. With these new terminology and particles, which are essentially, I'm just going to give you a hint, they're essentially what science considers virtual photons now. I'm just explaining them in great detail on what the fuck they actually are and how they're working and what all's going on there, okay? And spoiler alert, it works almost identical to the way I said it would 3 years ago when I did my lecture on virtual photons. It's almost identical. It's not 100% one-to-one carryover. Pretty damn close though, like 85-90%. I'm going to call that a victory, being so far back in the past. Paschon nailed it. Paschon, that dude, don't bet against Paschon. I wouldn't bet against Paschon. That dude's a fucking beast. Future Sean, who knows about that guy? He's fucking crazy. Me, I don't know, man. I'm just trying to live in the moment. But Paschon, that dude's got that shit down, son. You need to listen to that man. And, all right. Until next week, adios, muchachos.
Like, subscribe, submit.